So hello everybody, my name is Amir. I'm with Anybody Technology. I'm the host of today's webcast. I hope you can all hear me. Today Michael Putzer from the Laboratory of Biomechanics from the OTH Regensburg in Germany will give a presentation about the influence of vertebral geometrical parameters on lumbar spine modeling. The outline of today is I'm giving a short introduction on who and what is anybody before I will pass over the microphone to Michael, and he will talk, as I mentioned before, on the influence of vertebral geometrical parameters on lumbar spine loading. And after his presentation we will have a question and answer session where we both try to answer your question. So this is a reminder for you, if you have a question you should have a box in the GoToMeeting window that's called questions, and you can type in your questions during the whole time and we will try to answer them immediately, and you can so we will try to answer them immediately either by text during the webcast, or then we will have a couple of questions where we think it's interesting for the whole audience afterwards live for you. We will also record this webcast and put it on our homepage later on anybodytech.com. You can find the webcast later on. So very briefly, who is anybody? So there are different kind of anybody's. There's on one side there's the company Anybody Technology, which is based in Aalborg in Denmark. However, we have an office in Boston as well. Anybody Technology develops the Anybody modeling system and provides licenses, training, support, and maintenance with this for the software. We also offer consulting projects in various fields of biomechanics. On the other side, we have also the Anybody Research Group, and actually by now we have several research groups. There's one in Aalborg University, which is led by Professor John Rasmussen. They perform a lot of research in the area of biomechanics, ergonomics, sport, and automotive. There's also an Anybody Research Group by Professor Tony Petrella in the Colorado School of Mines in Denver, Colorado. He's also interested in biomechanics, orthopedic sports, and other areas. And there's the Anybody Research Group led by Professor Sebastian Dendorfer at the OTH Regensburg, where I'm sitting at the moment next to the presenter of today. And the research areas from this lab here are also in the field of biomechanics, orthopedics, gait, and several related fields. So very roughly about what is Anybody. So actually there are two main products from Anybody. One is the software itself, so that's a tool, basically a toolbox called the Anybody Modeling System. We usually use AMS as abbreviation for that. So this is basically the box, so this toolbox that you can use with all the functions in there. On the other side, there's also the Anybody Managed Model Repository, which is a library of applications and a library of body models. So you can choose body models in there to set up your body model. So in there are also the different body sections and segments in there. And then on the other hand, all those applications, so those activities of daily livings. So we'll find a model in there where a certain subject cycles on a bicycle, or another subject sitting on behind the wheel of a car, or someone performing, as I mentioned before, activities of daily living like lifting a box or walking or running. So if you combine both of those products, you can do a musculoskeletal simulation where input is the activity, so motion is input, and you apply this motion on a body model which consists of bones, joints, muscles, and ligaments. And then you get as output muscle forces, activities or power, and also joint reaction forces and moments. So you will know what is happening inside this human subject. There are also two animations. So this principle is called inverse dynamic analysis. And as I mentioned before, input is motion and maybe external forces. If you have ground reaction forces recorded on gate, in a gate lab, there's also a chance to predict ground reaction forces. Output is what is happening inside the human body. So all the muscle forces and activations will be computed using a muscle recruitment solver, and also the joint reaction forces and moments are computed. On the right side you see this full body model that's available inside the Anybody modeling system. I think this is the most sophisticated model that is available at the moment, with all bones in there and roughly 1,200 muscle fascicles in this model. You see also some details there. On the top side you see the shoulder, for example, and the lumbar spine, so this region where we focus on the presentation of Michael later on. Also hip, knee and foot in there. So the Anybody modeling system is usually used in various fields. When you look here on the top, so you see it's used in product design and optimization. So all products that are related to the human body can be optimized according to internal forces in the human subject. You can use it also for ergonomics in the area of in the automotive, for example, ingress egress into a sports car or sitting behind the wheel. So more orthopedic is then for surgical planning, evaluation and failure analysis. So you can model implants with spines or in all fields, in regions in the body. You can also use and transfer these loads that you compute with the Anybody modeling system to finite element systems like ANSYS, Abacus, or all systems that are there. And finally, you can do gate applications. We have a model called AnyGate that processes really easy gate trials. So finally, the workflow would look like you have an application. You see that could be any different kind of activity, and you can analyze in the Anybody modeling system to obtain muscle activities, forces, joint forces, to see what's going on in the human body. You can also use patient or subject-specific information. So if you have MRI or CT scans and the segmentation software like Mimics or Materialize or Simpleware, you can use this information to create a subject-specific model. So not use the standard bones and bone geometries and shapes that are in the standard body model, but create your own subject-specific model. And then you can output all the forces into a finite element model to perform further processing of this activity that you have there. There's also a hook to connect the Anybody modeling system to more advanced scripting languages like Python or other optimization softwares. And on the top left side you see there's also an interface to CAD systems like the SolidWorks to Anybody interface, which allows you to import a complete environment, which could be bicycle, for example, or like here an elliptical trainer. And then you have, or maybe even an implant, so you could have that as an environment for your analysis. So I will finish now with the Anybody modeling system and hand over to Michael. Michael is graduated 2010 with a Bachelor of Engineering from the OTH Regensburg in Germany. He performed a master after that and graduated 2012 with a Master of Science from the OTH Regensburg, and works since roughly 2011 at the Laboratory for Biomechanics of Professor Dendorfer at the OTH Regensburg in Germany. and he works on his thesis, PhD thesis, with the title Simulations of a Musculoskeletal Model to Determine Lumbar Spine Loading. His talk today is about the influence of vertebral geometrical parameters on lumbar spine loading, and I will hand over the microphone to Michael now. Please give me a second to do so.
Okay, hello everybody. I'm Michael. I'm the presenter of today's webcast. Okay, I've already been introduced, so let's start right ahead. First of all, let me introduce you to the whole problem. I think everybody knows someone who suffers from back pain, maybe suffers themselves from back pain. It's a very common problem in our modern civilization. The double number of spine surgeries in the last few years emphasizes this. There are different causes for back pain. One would be muscle tension or something more severe like degenerative disc disease or some fractures, or maybe or maybe a facet joint degeneration. On the right side of this slide, you can see a lumbar spine with a fracture, with a compression fracture at the L4 level. If you compare it with the healthy lumbar spine to the left, you see that the fractured spine tilts slightly to the right side. Okay, to correct this, a surgery has to be performed. Here you can see a picture, a radiographic picture with an applied fixation device. It consists of 6 pedicle screws and a linking rod. This rod has to be bended to pull back the spine into its original natural curvature. The surgeon has to decide about this curvature and therefore needs a specific training level. You may as well have noticed that it's not easy to identify everything on this radiographic image. Okay, therefore we have different problems. First of all, there are a lot of different causes for back pain, and they are sometimes not easy to diagnose. Then, as I mentioned before, the success of a surgery depends on the surgeon's training level, and we still have revision rates of about 10% as reported from some literature. Okay, what can we do to improve these problems? First of all, we need a better understanding of lumbar spine loading. The problem here is that we only have limited experimental data available. We can't just put measurement devices on each and every subject. Okay, another problem you've may noticed that before is that each and every subject is different. Therefore, we not only need simulations or something like this, we need subject-specific simulations. But before that, we have to define what exactly is a subject-specific simulation. On this slide, you can see 2 pictures of a model. The right side is a generic model, and the left side would be a subject-specific one. You clearly can see differences between them, and that would not only be the color. Now we've asked us 2 questions in the oncoming studies. First of all, as I mentioned, which geometrical parameters are critical for a subject-specific model, and additionally, we looked at ligament properties and looked for the influence on the loading. Before we can do some simulations, we need a model. We started from the spine fixation with force-dependent kinematics model from the Anybody repository. This model includes a detailed lumbar spine. The postures in this model are measured between the pelvis and the thorax, and for the lumbar joints, the FDK solver is used. If you don't know FDK, there have been webcasts previously which cover the possibilities of this solver. Okay, we not just did our simulations with this model, of course, we modified it. First step was to include a subject-specific vertebral geometry. Therefore, we altered the attachment points of the muscles and the ligaments, and we've aligned the axis of rotation with some recordings from a fluoroscopic radiograph. Such recordings are shown in the picture here to the left. Those recordings include a whole movement with the specific recordings, with the specific recordings of the movement. You can get the position of each vertebra from each recording over the whole, maybe in this case a flexion movement, and calculate from this movement the axis of rotation. Those data can then be used for a subject-specific model. This slide shows on the left side the axis of rotation of our modified musculoskeletal model, and the right side shows the results for one subject we've used for the axis of rotation. You can see here that the axis is always located at the upper end plate of the lower vertebra, slightly moved to the posterior side. I still wanted to remind you, if you have any question, just feel free to ask them and use the box as shown here on this slide. Okay, now we've got a model, and of course we have to validate it before we can use it in some simulations. This slide shows some comparison with experimental data from the group of Wilke. All postures studied here are the relative loading of the standing posture. If you look at the results, you can see that we get pretty good agreement over most of the postures, except the standing lift flexed posture. There's a larger deviation from the experimental data. The reason is that we don't know the exact angle at which the intradiscal pressure was measured in the experiments. This diagram shows all flexion angles we've studied in our model, and you can see that the lumbar spine loading increases over this flexion angle. It would be in the range of the experimental data at a very high flexion angle, but we also have the problem that the distance between the weight in the hand of the model and the body is also not known. Therefore, we have additional errors in our simulations. Okay, in our study we used 4 different postures. The first one is upright standing. The second one would be a flexion movement, as you saw here at first. The next posture is a lateral bender posture, and the last one would be some torsion about the vertical axis. This slide shows again all the studied 4 postures, and the table to the right would show the studied parameters in the during this study. First one would be the vertebral body width. You can compare those parameters with the 2 pictures on the lower side of the slide. Another parameter would be the vertebral body height, then the vertebral body depth. Then we've studied the transverse process width, the spinous process length, the pedicle length between the vertebral body and the vertebral arc, the disc height, the interfacet width, and the interfacet height. Additionally, we did some simulations with the curvature of the lumbar spine or the lordosis angle. Okay, now let's get to some results. This diagram shows those results for the upright standing posture. The y-axis depicts the force in percentage of the original state, and the x-axis is the interval used for the vertebral sizes. The outcome variable for all studies always was the loading in the L4, L5 segment, and we've only changed a single parameter over the study. This means we didn't, in the first part, we didn't combine any parameters. We only changed one parameter. And as a result, we only looked at always at the highest influence from the parameters. In this case, the highest influence comes from the vertebral body height and the disc height. The vertebral body height showed influences of about 10% and the disc height of about 6%. Now if we look to another posture, in this case it would be flexion, we see that additionally to the vertebral body height and the disc height, there's a large influence from the vertebral body depth. Now if we compare those results from flexion and upright standing to the other two postures I mentioned before, the torsion and the lateral bender posture, we would see that those two postures would exactly show the same behavior as depicted in this diagram. It always was the vertebral body height, vertebral body depth, and disc height. Okay, now we asked us what would happen if we combine two of those parameters. The results for this are shown here. First of all, let's have a look on the diagram to the left. Again, those results are for the upright standing posture, and the y-axis depicts the force in percentage of the original state, while the x-axis in this case shows the interval about the vertebral body height. The distribution over the lines in the diagram would be the interval about the disc height. This means the blue line on the bottom of the diagram is are the results for the smallest disc height, and the orange line on top of all the lines is all the results for the largest disc height. Now if we compare it to the results from a single parameter, we can see that they have some in common. If we take the results for the disc height, we see that the single parameter had an influence of about 6 to 7%, and if we look at the combination, we also see this change. Now let's have a look at the changes from the vertebral body height, and again the results from the single parameter changes of about 10% are shown in the combinations. If we compare those results for this posture with the other postures, we would see the exact same behavior. This means we always get a linear combination of the results from single parameters to combinations. The weight factor for each one would be, in this case, 1. Okay, as I mentioned at the beginning, we did some additional study. This was a study about the influence of ligament stiffness on the lumbar loading. First of all, the constitutive model for ligament force in any body is shown here. This formula means that the force in the ligament calculates from a stiffness factor, that would be K. EPS1 would be the elongation of the ligament, and LO would be the slack length. In our study, we only changed the ligament stiffness, and that for all lumbar ligaments at the same time, not for only one, but for all in the lumbar spine. We did those simulations with 3 different subjects where we just adjusted the kinematics. The study posture was a flexion movement. Okay, now let's have a look what's the influence on lumbar disc loading. Here you can see a table which shows the relative changes in disc loading. This means the loading between the smallest ligament stiffness and the highest ligament stiffness for 2 different lumbar motion segments, L3, L4 and L4, L5, and for 3 different subjects. The L3, L4 motion segment showed changes over the different ligament stiffness of about 9% for subject 1. L4, L5 here showed changes of about 17% for subject 1. For subject 2, these were 14% in the upper level and 23% in the lower level. Subject 3 showed 7% changes in the upper level and 18% in the lower level. You can see that an increase in ligament stiffness always leads to a higher increase in the lower level than in the upper level. Okay. Another thing we've noticed in this study was that increasing ligament stiffness leads to changes in the joint angle of the flexion, of the last position of the flexion movement. The diagram shows the ligament stiffness on the x-axis. 0 would be the smallest ligament stiffness, 100 would be the highest ligament stiffness. The y-axis shows the joint angle of the flexion movement. And if you look at the 2 blue lines and the black line, you see that they decrease over an increase of ligament stiffness, and the L4, L5 line and the L5S1 line, the red and green line, increase over an increase of ligament stiffness. This diagram tells us that if ligament stiffness is increasing, we also get a shift of the motion to the lower segments. Okay, now let's get to the conclusion of our 2 studies. The first study showed that measurements of vertebral body height and depth, as well as the disc height, and additionally the curvature of the spine, which has not been covered in this presentation, could be sufficient to build subject-specific models. The advantage of this would be that those dimensions can easily be taken from radiographs. This would mean a lower radiation exposure for a patient or a subject, and we would have fast access to subject-specific models in preoperative planning. The second study showed that an increase in ligament stiffness could lead to an increase in disc loading of up to 23%, and that the motion shifts to the lower lumbar parts. A possible clinical implication from this would be that degenerations affect the spine kinematics and kinetic in different parts of the spine. Okay, that's it so far from me. If you have any questions, still feel free to ask them. And now I will give back the microphone to our host.
Yes, Michael, thank you very much for this interesting presentation. Okay, thank you, Michael, for this interesting presentation. So it was very interesting to see all your results. looks like the accuracy depends very much on the application, as you have seen. So it might really be possible for certain applications that mostly X-rays could be enough for some models. So we will, of course, look further on how your study will progress and how what your future results will be in the next time. So before we move on to the questions, I see my colleagues here are very busy answering questions in the questions from the question box. We have a couple more questions for Michael later on. So there's a lot of opportunities to get in contact with us and to get more information about anybody. So we have the homepage anybodytech.com, where we have a list of events and all the dates in there. We have a list of publications, so you can see who has previously published data on using the Anybody modeling system. We have also the homepage anyscript.org, where you can find a wiki and the forum for discussing problems and posting questions there as well. And there's a YouTube channel by Anybody Tech where we post videos, help, demos, tips and tricks, and also this webcast will be published there within the next days. There's also the chance to get in contact with Michael Putzer and Professor Dendorfer. So their homepage is lbm.rcbe.de, which stands for the Laboratory of Biomechanics of the Regensburg Center of Biomedical Engineering. There's also the chance, if you're interested in, to come and listen to our next webcast, which will be on May 13th, which is in a very different field of research. So we will go, we have a presenter from Tokyo who analyzed several different commuting techniques, like in the train and a motorbike and different forms of transportation, and he will look from a musculoskeletal aspect into that. We will be at several conferences, for example, spine conference in late April in Miami, Florida. One of my colleagues will be in Shanghai soon in May. We have a conference on neurorehabilitation in Denmark, actually, in June. And Professor Dendorfer and his team, and also we from Anybody, will be, of course, at the World Congress of Biomechanics in Boston in first week of July. So if you're interested, you can contact us and we set up a meeting and discuss maybe also Michael's results in there if you're interested. If you want to get more into musculoskeletal simulation and modeling, there are training courses. The one in May in Denmark, in Aalborg, Denmark, is already fully booked, but there are still a couple of slots free. And the one in Golden, Colorado in early August. And also there's another course in September here in Regensburg. So